and maybe say a little bit more on SLH formalism. So I could have called this even more SLH, but I settled for Introduction to Quantum Stochastic Processes. So what I'll try and do is maybe pull in some more people from the quantum optics community just to show them how the stochastic calculus and quantum stochastic calculus works, but also maybe some of the mathematical audience who possibly are a little bit overwhelmed with the analysis, so I'm going to drop much of that and just concentrate largely on algebraic properties. Okay, from this morning's talk, we had the notion of a channel. I'm going to work in the Heisenberg picture, so I'll call my map J, but it's really the T star, the dual map that Mikhail introduced. So the idea is we take some observable x, or some operator on the system, and we churn out another one, right? And it's a linear map. What's sometimes referred to as a super operator. We want it to be a star map. Stars are daggers. If I do change back to stars, just understand. The other property we want is positivity. And the reason for positivity is that the dual map T has to map probabilities to probabilities. All right? So what does positivity mean? If we have a positive operator, it gets mapped to a positive operator. Now, the issue of complete positivity comes about as follows. We might have, say, a second channel which we want to run in parallel with the first one, and you can define very simply how you run these in parallel. It's just a map. The basic idea is you take x tensor y, or any linear combination of these, so it's enough just to define it on this. Well, x gets taken to j of x on the first factor, y gets taken to k of y on the second factor. And of course you want this positive as well. So running these things in parallel, you also want to be positive, but that's not actually immediate from just positivity alone. So basically what you want is a category of maps satisfying this, with the addition requirement that any two from the category run in parallel will also be in the category. That's where complete positivity comes into it. So one thing you could say is that J is completely positive if for any other completely positive map here, J tensor K is also positive. That's a bit circular, that definition, but fortunately we can give another definition. Just build it up. For instance, we could just take the second system here to be an n-dimensional system and K just to be the identity map. In which case this is fairly easy to describe. The operators they act on, we can think of this as the space of n by n matrices whose entries are operators in whatever our initial Hilbert space was. So what this guy would do is just take each entry, apply the super operator to it, now it turns out that positivity alone of J doesn't guarantee that this object here, so if this is a positive operator, it's not necessarily the case that this is a positive operator. So you need this extra condition. And what we say is J is n positive if this thing is going to be positive, all right? And J is completely positive if this thing is positive for all integers n. And it turns out that's the requirement. That defines the category. If something's completely positive, tensoring it with any other completely positive super operator will give you a positive, in fact, completely positive mapping. If and only if, yeah. So is this. That's the definition. So we're going to look at the category of completely positive maps. Oh, these are well-known results, yeah.
No, that is, yeah, but I've never seen a proof. Is it difficult to go from any operator that is positive for any K, the previous one?
I don't know. These are well-known results, which I know, but
I always
yeah.
do it, but I don't know what I never proved it.
Yeah. Okay. So I really just wanted to remind people of why complete positivity is so important. Basically, it tells you the type of morphisms you should have between algebras of operators in quantum mechanics. And what I want to lead into is the notion of quantum dynamical semigroups. So these are semigroups of CP maps. I'm not going to do any sort of analysis, but typically you formulate this as being weak star continuous if you want to know the conditions. And the idea is that the composition, and as we heard from Mikhail this morning, the composition of CP maps is again CP map. So we want basically a dynamical flow like this. At 0 it should just be the identity operator. And a fairly crucial result of Lindblad on one hand, but also Greeny, Kosakowski, and Sudarshan is to characterize the generators associated with these semigroups. So call this GKS, Greeny, Kosakowski, Sudarshan, Lindblad generator. Sometimes just Lindblad generator for short. Again, most of you are familiar with this, so I won't dwell on it too much. H is just the Hamiltonian. So this bit here is familiar from quantum mechanics, I hope. This is another super operator which takes the following form. if this bit is a derivation, this is somehow related to taking commutators of commutators. So it's, in a sense, second order. So it's not a derivation, it's dissipative. Now, so what we have is generally a convex combination of these plus a Hamiltonian term. Right. Now, all of a sudden I'm going to get very classical and tell you some classical probability with a little bit of quantum thrown in. So what I'll do is I'll start off with the simplest type of distribution we have in the continuous setting, the Gaussian. So I'll tell you everything about the Gaussian you need to know. Looks like that. Characterized by two properties, the mean and the standard deviation. So I often write this as n mean mu, sigma squared is the variance. Okay, the probability function for this has a probability density that's what it looks like. You get a lot of information from just looking at the moment generating function. If x follows this distribution, its moment generating function is the following. And it's got two non-zero cumulants, the first which is the mean, the second one which is sigma squared, the variance, and then it stops. There are no higher cumulants. The cumulants are the terms in the exponential here when you expand out. Okay, and from that I want to go straight into the Wiener process. The Wiener process, what mathematicians call Brownian motion, and as Robin told us, there's no momentum, so it's not a really great idea of Brownian motion as far as physics is concerned, but mathematical Brownian motion, or the Wiener process, it's basically defined as follows. It's a Markov process starting at the origin. We'll have time running this way. I'll write it as W for Wiener. The sample paths of unbounded variation. So let's suppose there's a sample path. So we observe it up to, say, a particular time t. And because it's a Markov process, what you need to do is to say, well, given the state at time t, how do we predict where it's going to be in the future? So we look at some time tau into the future. What's the probability distribution for the Wiener process to be anywhere in space, given that we know its history up to time t? Well, the answer is it's a normal distribution, which I'll draw on its side like this. Its mean corresponds to just the last recorded position of the Wiener process, right? And the full history beyond that, earlier, is totally irrelevant because it's a Markov process. The other thing you need to know is the variance, and the variance is time tau, okay? So basically, how far have we gone here? Well, the root mean error is square root of tau. And the notorious thing is, of course, if you let tau go to 0, root tau over tau goes to infinity. Yeah?
So if you have a drift, would that immediately constitute a non-Markovian process? Because you have a drift.
No, if it's a deterministic drift, no. I mean, This is the simplest case, but you could have a diffusion with a drift. Yeah.
And that would just go straight into your WT.
This thing saying that there's no drift actually corresponds to what Robin was saying yesterday is the definition of a martingale, right? The fact that you're not drifting away. If you average where you're going to be in the future based on what you know up to time t, your best guess is on average going to be your last position, right? So that's the martingale property. Right. Because the increments, and we're typically talking about future pointing increments, Ito increments, because the increments are mean zero with variance equal to just the time step, so dt, you can actually develop a calculus around this, the Ito calculus, where you're basically allowed to make these substitutions under the integral sign. So I'll occasionally drop the label t, but understanding it in there. If you were given some function of Brownian motion at time t, maybe I better put it in, and you wanted its increment, this is understood as future pointing. Well, what you do is use Taylor's theorem, but you have to go to the second order in Taylor's theorem. It turns out you can truncate here because the third order terms are negligible in the calculus. So the increment dw is not a true infinitesimal. And you have this remarkable formula due to Ito, which says there's an Ito correction. So this Ito formula has, of course, been applied quite a lot. For instance, stochastic processes in financial mathematics, the Black-Scholes equation. But we're going to use it for something more useful, namely to do some quantum mechanics, right? So what I'm going to do is to look at a rather unusual type of dynamics. It's going to be a stochastic quantum dynamics driven by a Brownian motion. Okay? So what I'm going to do is to say, I'm going to consider some operator depending on a parameter t and make it as unitary looking as it possibly can. Say take some operator E, which we take to be self-adjoint, bounded if we don't want to do any analysis. And rather than having e to the I, this operator times t, I'll stick in the Brownian motion process in its place. Okay, other than the fact that this is an operator, we can think of this as really a function of omega. Sorry, of w. And just using Ito's rule, differentiating the exponential just brings down the exponent. So we have a term that looks like this, but then we have the second order correction, which looks like this. We still have the exponential, which we'll just reconstitute as u over here. Okay, now, look, we know it's unitary, right? So we don't have to worry. But if you look at this stochastic differential equation here, you might get a bit edgy if you saw this first of all, and you say, well, hold on, what's this, right? It looks like a drift term. Indeed, the whole evolution is unitary. If we average this, which is not typically a physical thing to do, if you did average it, this would average to 0 and you'd be left with this, and it would look like a decay. But in a sense, we're saying, look, we have this environment, it's a Brownian environment. We could think of it actually as a subset of something non-commutative. We're basically tracing out. We're averaging something out, and then you'd lose unitarity. Keep it simple. What about the Heisenberg picture associated with this? We've tended to call this Heisenberg-Langevin because it'll actually end up as a stochastic differential equation. If you did this, you have to use the Ito calculus as usual Leibniz rule, but there's a correction. And again, it's coming from this second order fact that the W squared is not negligible. And if you use this equation, and its Hermitian conjugate, you find a commutator bit with the operator E. The T here just the same as over here means we're putting U and U star either side. That's the W. So this is the fluctuating, or this is martingale, if you like. So this averages to 0. So for instance, from this bit here, the Ito correction, you actually end up with a term like this. This will be a dt term. And coming from here and here, the dt part will be 1/2 e squared. This again is in the Heisenberg picture, that's dt. And what we actually have in here is a Lindbladian.
What's the T
Wait.
for commutator and anticommutator?
Hmm?
What's the T in the commutator? The label.
T.
Yeah.
Oh, T just means we're moving into the Heisenberg picture. Because I'm too lazy to write U star and U either side, right? Yeah?
To motivate the UT you started with,
Hmm?
where is it coming from?
No, I'm just solving stochastic differential equations. It's to show you the classical version first before we go on to the quantum, right? So basically we've got a diffusion in here, Brownian motion. Now in models I'll show you later, you have a sort of quantum diffusion due to the creation and annihilation of quanta. This would be, if the quanta are taken to be bosons, this would be something photoemissive. You don't see it because there's a combination that they're somehow packed up in the Brownian motion. Okay. The next distribution, second most important distribution in classical probability, is the Poissonian distribution. All right, that's a discrete distribution. It takes integer values. It's basically counting things, so it starts from 0, 1, 2, 3. In general, the probability for it to have a value n is the following. If we have something which has a distribution like this, well, first of all, its moment generating function I'll write n for the variable. You have to sum the following series, which you can do easily. It's e to the lambda e to the t minus 1. So it's an exponential of an exponential. If you say what are the cumulants, so expand out what's in first exponent here, you actually find that all the cumulant moments are equal to lambda. So the mean is lambda. The variance is also lambda. And all the cumulants after that are lambda as well. Now it turns out, just as with our construction of Brownian motion in terms of the Gaussian, we can construct a classical stochastic process on the Poissonian. So this is the Poisson process. The idea is similar to what we had over here for the Wiener process. It's going to be an independent increments process. It's going to start from 0. We're going to define it in terms of its transition probabilities. What happens is that if we're observing it, what we can think of certain times where it's making jumps, and these times are random. They follow a particular type of distribution which will come out from the particular structure I'm going to show you. So as usual, we say, well, we're given the history up to time t, right? So it started off with a count of 0, it's jumped to 1, 2, 3, 4. There have been 3 jumps. We don't know what's happened in the future, but what we'd like to say is that if we did look at it at time tau later, what would we get? And we just do the same sort of thing as before and say, well, the distribution we get is going to be a Poisson distribution. So again, I'll draw the probabilities on the side, right? So we could have either stay the same, a transition of 1, a jump of 2, a jump of 3, so on. So basically what we have is our last recorded value, call it nt, plus something that's Poisson, and it's basically proportional to the amount of time we're looking into the future. Okay? So this one's always going up. It's not a martingale, but there is quite a clear transition mechanism, and it only depends on your last known state, not the previous history. So it has this Markov nature to it. Now what you can show is that for a small time step, so tau is infinitesimal here, then your probability to have more than one jump is negligible, right? In fact, that's another way of characterizing the Poisson distribution mathematically. So basically, for the infinitesimal changes in the number here, over any infinitesimal period, it's either going to be 0 or 1. So we either stay the same or we jump. The chances of getting 2 or more jumps in an infinitesimal period are negligible, and you can forget about them in the calculus that follows. So this equation is basically saying that the jump, dn, can either be 0 or 1. Right? What's the analog of the Ito formula here? Well, again, use Taylor's theorem. Here we'll have the nth derivative of g we'll have the nth power of the increment and going from 1 to infinity. All right? But then you see the n squared is the same as the n cubed will be the same as the n squared, which is the same as the n. So all these powers are actually just the n. Okay, so we can sum everything else and leave this alone. And we end up with this formula, okay? And naively, just what it's saying, to interpret it, what's the change in any function of the counting if we just look an instant into the future? Well, if there's no jump, then dn is equal to 0, so there's no change. If there is a jump and this is equal to 1, well, all we've done is to change g from its value at count t, and it's increased by 1, right? So, what do we do with this? Well, we do some random quantum mechanics, right? So this is randomized quantum mechanics. Similar to the construction we had here, what could we do? How can we get a unitary process driven by jumps? Well, we have to take something unitary to begin with and just raise it to the power of the Poisson process, right? Now, for this to work, S has to be unitary to begin with. So what you can think of is that at various random times, we're basically applying this operator S. And it has to be unitary, so everything's unitary. So what do we get at any time t? Well, we just count the number of random times that have occurred, so it's S applied that many times. What's the stochastic differential equation it satisfies? Has to be this, okay? Take out s to the power of n as a factor, but that's just u. Okay? If you want to know what happens in the Heisenberg picture, well, with the same development here, what happens, just plugging in this equation, using the fact that the square of the increment is just the n again, and using the unitarity here, this actually takes the form of the following. S star xs minus x, and then we move into, I'd call it the interaction rather than the Heisenberg picture, but anyway, putting u star here and the u here. This bit, incidentally, is also a Lindbladian. Maybe it's not obvious, but just putting S in as your collapse operator, as it's called, and using the fact that S star S is the identity, you actually find that it is of Lindbladian form, right? These are not martingales, by the way. If you average this, it's nu dt, where nu is this parameter up here. That's called your Poisson rate. You can make inhomogeneous Poisson processes as well. So we've seen that somehow randomizing these stochastic evolutions have led in a natural way to some of the Lindbladians you can come across. Right? Again, if you said, well, what's the average of the increment here? Well, we'll have the average of this particular Lindbladian acting on x moved into time t, all times the n, which averages to nu dt. Okay? So what we've been doing is to construct basically you can show that we move into the Heisenberg picture and then just average out the noise, we're getting a CP map. And it's a semigroup, right? We even see the Lindblad generators. Okay, so in a sense, the quantum stochastic calculus came about from a way of trying to do a general theory of dilations of CP semigroups, right? So let us say something about quantum stochastic calculus. I'm going to cut quite a few corners here. So most of the action, as we've seen, takes place in a Fock space. Let's call it F. We have some underlying Hilbert space H. And what we do is we take a direct sum as follows. There's a vacuum space, there's the one particle space, the two particle space, which is just the tensor product of the Hilbert space with itself but symmetrized, then a third order space, so that would be threefold tensor product symmetrized, and so on. We'll introduce a specific vector which corresponding to having the vacuum, right? That's what this space is, but no amplitude associated with the one particle, two particle, three particle states, and so on. There's the exponential vectors. These are non-normalized versions of the coherent states. So to use Robin's notation from yesterday, I like these as E for exponential. B will just be some vector in the one particle space. So again, it's the vacuum part. Beta is the one particle state. We have a non-trivial two particle state which looks like this. And so on. Okay. Now I'm going to do this fairly formally. Our one particle space is just going to be square integral functions because we're going to think of pulses. And I'm going to introduce a pair of singular operators. As Robin would point out, they're not really operators, they're some sort of densities, satisfying singular commutation relations of the following type. So basically, some sort of white noises parameterized by time and satisfying singular commutation relations. Okay, so Robin tried to tell us that there's no physical interpretation for this, but I hope quantum optics people will say, well, if these exponential vectors are just Bargmann vectors, non-normalized coherent states, then applying the annihilator, what it's really doing, I suppose beta is a nice test function, it's just pulling out the value of the function at time t. Okay? So we've some reservations from this, which Robin mentioned, but you generally get the idea. And maybe better just mention before we move on. The rather curious 1 over root n normalization in these exponential vectors is such that when you work out the overlap between two of these states, you're actually just getting the exponential of the overlap of the one particle test functions, right? So as usual, these states here, the exponential states, are overcomplete. Now, what I'm going to describe in a very hand-waving way, not at all like what Robin did yesterday, is just to say we'll work with better defined operators. This is a creation process, right? We'll have, this is an annihilation process, there'll be a creation. And we'll also introduce something which counts the number of quanta over an interval of time 0 to t, which will look like this. Some people ask, what's the parameter t if it's supposed to be time? I guess in our SLH theory, we're thinking of a system maybe fixed at the origin. So B of t is something to do with the field externally. The field is moving in and passing through our system at the origin, and B of t is the annihilator for the field that passes through the origin at time t, right? So if you want some physical intuition as to what the time is, that's what it is. So if you think of a system at the origin, this thing is describing the annihilation of a photon at the origin as the field passes through somewhere between the time 0 to t. This is the creation in that time period. This is the number, okay? And one of the remarkable things, remember, if we took our one particle space here, h, just to be the complex numbers, then we have the harmonic oscillator. So this is everything you learn about the harmonic oscillator. The vacuum will just be the vacuum of the harmonic oscillator. Here we'd forget about indices t and s because it's zero-dimensional, right? Your exponential vectors really just are the Bargmann states, right? So what we've done is to have many modes. In fact, we're interested in having a continuum of different oscillator modes. All right, so we could, for instance, look at the following combination. It's a quadrature, B plus B star. And this has a Wiener distribution. I better say this is a Wiener process vacuum state. Crucial to this interpretation is the fact that at different times these commute with each other, so it's essentially classical. You can introduce a Weyl displacement operator. This is a unitary. Do it this way. And this effectively displaces your operators in the same way as in more familiar quantum optics of just one or a few modes. It'll displace by the pulse shape B, right? So for instance, just some simple formulas. If I displace the vacuum, I end up with the coherent state. I have to have the normalization here. So that's just the displacement. If I want the moment generating function for something like this in the vacuum state, well, I just get the Weyl unitary and sandwich it between matrix elements here, the vacuum. And that's all that survives, right? Because I'll have the vacuum, which is coherent state with intensity 0, overlap with this, doesn't really matter what it is, it's an exponential vector. I'm just going to get identity. So this is the following, okay? And this would be the moment generating function for a Wiener process. So using everything we've learned about the Wiener process, if I did something like say, well, I want something like this. Better make beta real, but the exponential of a classical Wiener process, if you wanted its moment generating function, would be exactly this. The fact that beta was complex actually tells you that there's more than just one Wiener process. So for instance, I could define a whole family of processes. These are called quadratures. For each fixed theta, they commute with themselves for different times. So each of these quadratures, once you fix the angle theta, is a self-commuting process. And in the vacuum state, it's going to be equivalent to a Wiener process. The problem is that these don't commute for different thetas, right? Another lemma is that if I chose the coherent state, this number process will actually be a Poisson process. And to see that, I again choose something to average Okay, the coherent states are just the normalized Bargmann states, exponential states, so I need to have this correction here to ensure normalization. Now here's the crucial property. This exponential here, with respect to the gauge process, how it's going to act on the coherent state, it's just as in the single mode or finite mode case, it performs a unitary rotation, right? So locally, it's multiplying beta by e to the if at each time t. And then we work this out using this formula here for the overlap of the coherent states, the exponential vectors. And you find this is e to the minus beta squared. There's another e to, it'll be beta e to the if beta again, it's an exponential of an exponential. And again, you'd identify this as something Poissonian, right? Now, how much time have I left, Matt? 5 more minutes. Okay. Right. So in the time remaining, I'll tell you about what the quantum stochastic calculus actually is in physicist language. We're going to fix a Hilbert space, which is going to be the Hilbert space of our system, and we're going to couple it to the environment. So this is the Fock space. I'm going to be very loose here and drop index or parameters t from this, but these are all understood to be processes time valued. So we're interested in what you could call quantum stochastic integrals. So processes x, which satisfies some stochastic differential equation of the following type, I'll assume that the coefficients here are all processes themselves and they're all adapted, which means that they'll effectively commute with future noise. I can make that a lot more explicit. You saw a little bit in Robin's talk, but for the sake of brevity, I won't dwell on it. And I'm going to say that there's another way of writing this. Which is using the fluxion notation. This is a little bit illegal, but we're in the Newton Institute and Newton used to do this type of stuff, so I guess I'm in good company. And as Robin said yesterday, right, we can choose some vector on a system, an exponential vector for the Fock space, and then a similar thing here, and look at this average. Because everything's in normal order here, when the exponential vectors coming from the right here hit any of these singular operators, they're just pulling out the value at that point. So for instance, the first element of this, according to Robin's definition of what this bit means, it's the average of this. The coherent state coming from this side will bring out alpha t star, and the one coming from this side, when it hits this, will bring out beta t, and that's all the t, plus 3 other terms. And then you say, well, this is just what we're calling x dot here, right? Because that's what the b's and b stars do. And the problem is, what we've got is a Wick-ordered calculus, which tells us that the x can be interpreted as x dot dt. And the problem with Wick-ordered calculus is when it comes to products. So for instance, what do we mean by the x times y? To be interpreted in the Ito calculus, or as a Wick-ordered calculus, what we'd have to do is present this as something normal ordered with these singular terms. So the natural thing is the following, where we deliberately put the b not here but this side, and likewise the b isn't here, it's this side of the y, but this is not equal to, for instance, x dot y dt, because of the fact that we normal ordered things, right? So what in fact you get, the Ito rule in its most general form, and this is what comes out of the quantum stochastic calculus, is really just Wick ordering in disguise. In fact, what you get, the following is valid. All right, that turns out to make sense. So we can define this properly as Ito, and this is Ito, but we know that this isn't exact. There's an additional term, which is the Ito correction, and well, these are both stochastic integrals. The correction term looks like that. So special cases, we've got dB by dB star. If you see what survives, it'll actually be dt. dB by d lambda is dB. These are the non-trivial ones, and they're the ones out of Wick order that you have to Wick order to get them back. And d lambda is d lambda. Okay? So now we just do the same trick as before. So this is unitary quantum stochastic evolutions. We say what we want is, there's some operators G11 d lambda, G10 d b star, G01 dB plus G00 dt times u. if we want this to be unitary, just as in the Proton case, it has to look as follows. It's S minus 1 where S is unitary. G10 is our collapse operator, or coupling operator. That can be pretty much arbitrary. But again, just using the type of Ito calculus we've seen up to now, we can find that G01 won't be free. It'll have to take this form minus L dagger S. And finally, the dt term is minus 1/2 L star L. So this we've seen before in the diffusive case. And it's determined up to some skew adjoint operator here, so basically H has to be self-adjoint. Okay, it's probably a good place to stop.
Okay, thank you very much, John. So, any quick questions before we wrap it up?
Well, just a question physically about, say, a quantum stochastic process. Do I think of it as a quantum that turns on sort of like at stochastic intervals, so to speak? So it's a quantum process driven by a stochastic one, or is that not?
Ah, you're talking about subordination or something like that. Is that it? No. These things have a life of their own on the Fock space, I'd say.
Okay.
I don't know if you'd agree with that, Robin. I don't see how you could get this as a subordinated. It would have to be a subordinated classical process, but these things are utterly quantum at their heart, right? Yeah.
So are there any computational advantages of sort of going this route opposed to the master equation, or do you end up with...
The master equation is a derivative of this, right? Once we have the unitary, we can start saying what happens in the Heisenberg picture. So we now take an operator. I should say x times t means something very specific. We take an operator x in the system. We take the identity for the Fock space, so the environment, and then we just use this unitary process, which basically depends only on the part of the field up to time t that's passed through the system, right? So it is going to be adapted. Can I remember it? The lambda term looks like this. Careful to put t's on these. Again, these are all martingale terms which will average to 0 in the vacuum state. So approximately, I think these are correct. That's the annihilation part. And then there's the dt bit, the only part which would average to something different from 0 if I take the vacuum average here. That's the Lindbladian, okay? And it's the Lindbladian with L as collapse operator and H as the Hamiltonian. Okay? So the master equation, all the master equation is doing is saying that if I now want to average everything out, what do I get? So I just average this out over the vacuum. This is actually a partial trace, right? I'm still left with an operator on the system, okay? That's my semigroup. And it has the Lindblad generator like this. So if I now want to pass to the dual picture, which is the Schrodinger picture, what I'd get is, basically I want to say, well, I fix any initial state on the system, and I want... That's a trace, yeah. I want to say, well, actually, I should be able to come up with some time-dependent state here, which just acts on the original x, which I can do by linearity and duality here, and rho will satisfy the master equation, right? Which will look like this. The star here just means the adjoint of this going from bounded operators to trace class operators, just using the usual duality. So this is, if you like, the quantum version of the Fokker-Planck equation, right? So in this sense, the master equation isn't the starting point. It's something you can get to as a result. So the model gives you a full unitary model for the system, but also the environment that it's been interacting with. You can also add in... Yeah, what I was going to add is that you can also measure the output of the field and do, you come up with a stochastic master equation. Stochastic master equations are also derived from the input-output theory. I haven't told you what the outputs are. I think we're out of time.
I guess you'll pick that up again on Wednesday or Thursday.
That's right, yeah.
That's why I said in my talk yesterday that once you've got the SLH parameters, you can easily determine the master equation and the filtering equations, right? They're just theorems now in the papers that you can look them up, right? Okay. So the more fundamental model, I guess, is this one, I think. And that's much more in the spirit of conventional engineering, actually, is to have a differential equation model. You know, differential equations are used widely in engineering, right? And then when you want to calculate things, you calculate the Fokker-Planck equation.
Right. So at the moment we've got the system, the noise coming in as input. I haven't told you the output story, but you've now got a system state, well, an input, state, output model. Well, that's a story for another day.
Yeah. And it's also from the point of view of networks, when you've got multiple components that you're putting together, it seems to be more natural to do it at this SLH level, QFT level. Because once you're doing a master equation, you've made some decisions about what to average out, right? You're averaging out a lot of external stuff. If you've got a network of interconnected components, it doesn't make sense to do that at the modeling level, right? So you only do the master equation when you want to actually calculate something, really. Whereas if you have, right, it doesn't make sense to have a master equation for each component and try to combine those master equations together, right?
Okay.
Unless they're all independent, right? Okay, thank you, John.
Right, cheers.